Hi, my name is Ronnie, and in this module we'll look at some design features that can add value to your 3D printed part. Let's start by looking at the agenda for this module. First, we'll look at why we should design for 3D printing. Then we'll look at some of the features that can add value. And finally, we'll look at 9 different ways where we can generate added value by designing for 3D printing. First, we'll look at how we can get the most value out of our 3D printed parts and the design process behind them. If we start in the bottom of the pyramid, then the 3D printing technology started as a tool for rapid prototyping. Here, we usually have a low volume of parts. The next step is that we go in and replace an existing part with a 3D printed part without changing the design. Here, we get a little bit of added value out of the 3D printing technology. In addition, we can go a further step up, and here we'll look at part consolidation. This is where we go in and take several parts and consolidate them into one part, thereby utilizing the 3D printing technology and adding more value. And if we jump to the tip of the pyramid, then we're in the category of design for 3D printing, where we start to create new products. In this module, we'll focus on the tip of the pyramid, and we'll look at different examples of products that have gained an advantage by being designed specifically for additive manufacturing. I'll quickly go over the 9 overall features, and then afterwards we can go in depth with each of them and look at some cases where these features have been used. If we start in the top left corner, we can see that we can use 3D printing to get some new functionality into our parts. We can also start to make some lattice structures that weren't possible before. We can start to optimize our components towards lightweight, thereby making them both lighter and stiffer. We can begin to make part consolidation, where we put more parts together in one. We can make channels and tube connections that weren't possible before. We can also make mass customized products in large numbers without added expenses. And in addition, we have the possibility of making some components with thermal properties that weren't possible before. The 3D printing technology also gives us a large extent of design freedom that we can utilize. And finally, the computer is one of the really strong tools when designing for 3D printing. So we'll also look at how we can use that. If we start to the left and assume that we need to design a product, well, then we can take the balls from the top row and add them to the basket. Thereby we add some value to this product, which justifies the use of 3D printing. The more balls that we can start to put in this basket, the more value we can add to the product, and the more we can justify using 3D printing as a manufacturing technology. Let's take an example to show how these baskets can be used to design a part. And remember, the more features that we can get into the basket, the better the product we get. So if we take a relatively simple part like this nozzle to make cookies, then it used to be made out of 6 parts, but with 3D printing we can make it in just one part. So here we have some part consolidation. Furthermore, the flow through the nozzle is more smooth and even, and we can get that by utilizing some of the possibilities of making special channels. And finally, we can use mass customization, where depending on the cookie that you want, we can quickly change the design of the nozzle, so we get a nozzle that fit the individual cookie that you want to make. Now we've taken a brief look at why we should design for 3D printing and how we can utilize these features. Now we'll take a closer look at the 9 different features and see where they make sense by looking at some different cases where they've been used. And what we'll see when we dive into these cases is that a lot of these cases actually utilizes more than one feature. We'll start by looking at part consolidation, which essentially is about reducing 2 parts to 1 part. We can illustrate this with the toolbox to the right, where on the one side we have a toolbox consisting of a lot of bolts and joints, and we can actually reduce that to only 2 parts. And the new toolbox has the same function, only fewer parts. This is interesting because it saves a lot of assembly time, and we don't need to have as many spare parts in stock. Often we can also save some weight, and it reduces the amount of contact areas, which could be of interest to some industries. Here's the first case to illustrate part consolidation, and this is the layout that I'll use for all the cases. So in the top right corner we can see the basket, and we can see the features that we added to the basket in this case. This particular case was about reducing the number of components in the part because there were way too many assemblies and joints. Because of that, the part was hard to clean, and since it's featured in a machine where it's in contact with fresh meat, it needs to be cleaned every day. So the more simple we can make it, the more time we can save on cleaning. Therefore, the design ended up looking like in figure B, where we've taken the 42 component and reduced them to just one component. We have no assemblies and we've reduced the weight by 50%. And since the part is moving a lot and really fast, that's an advantage too. And we've done that by 3D printing in titanium. Another case is this robot gripper, which conventionally consists of a lot of parts, as you can see in figure A. In this case, it's approximately 72 parts, and we can make that much more simple by 3D printing it. In fact, we can actually reduce it to only 8 different parts. We have some suction cups, some pneumatics, and then just the gripper itself. Another cool thing about this gripper is that it's actually generated in an online software. So we use computer power to design it, and that way we can design it in just under 10 minutes. Now we'll take a look at how we can design channels and tubes, which weren't possible to design before we had the 3D printing technology. So why are channels an interesting feature for 3D printing? Well, if we look at the first picture, then this is how we make holes conventionally. We drill in different directions to make some channels, and then we plug the holes afterwards to shut off the channels. But if we then look at the next picture, this is how we would do it with 3D printing. And as you can see, it's much more smooth around the edges. So why is this interesting? Well, if we look at the figure below, we can see how the speed of a fluid passing through a channel changes depending on how soft a curve it needs to pass. So if we have a 90-degree turn, then we're at 18.2 meters per second. But if we then optimize the channel, well, then we reduce this by 3 meters per second, and that means that we have less of a pressure drop and we need less energy to push this fluid through the channel. This can be used when we have some fluids, for instance water or oil, that needs to pass through a channel. Here we can then reduce the pressure needed to push the media through the channel, thereby saving energy. So that's why it's interesting to look at these channels. The fact that we can make channels with 3D printing that are curved instead of just straight has been utilized extremely well in this case from the German company SMS Group. This is a spray head for maintenance of large injection mold. It mixes air and lubricant inside this manifold. And if we look at how it was made previously, then we can see in the picture to the left that it was a massive block consisting of a lot of different parts. That means that when we start to look at 3D printing, there's definitely a potential for reducing the weight. If we then compare it to the 3D printed version to the right, we can see that this is much smaller, so there's definitely a weight reduction. We've also optimized the flow, and it's easier to get the lubricant to where you want it because we can control the placement of the nozzles much better. By 3D printing this spray head, it's now possible to print it in metal, but we can also print it in nylon with the powder bed fusion technology, and it can actually withstand the high temperature. In fact, this is such a good idea that SMS Group has chosen to patent this solution because they see a great business opportunity. One of the places where these channels are particularly interesting is in the injection molding industry, where 3D printing allows us to have what we call conformal cooling. If we look at the first picture to the left, then this is how we conventionally made channels, by drilling them all out. Now that we've started 3D printing the channels, then we can make them curved. And conformal cooling is all about getting these channels as close to the surface of the metal block as possible, because then we can cool our plastic part much faster when we cast it. In a minute you'll see a picture of what such an injection mold looks like. But if we look at the cooling effect, then we can see in the picture in the bottom left that the conventional mold has a much higher temperature than in the 3D printed mold. This means that we can actually use the 3D printed mold to produce even more parts than it was previously possible. This is also the focus of the next case, where we'll look a bit more in depth into how this is used in real life. This is an example of how we make a shield for a high pressure cleaner. Previously, as we can see in figure A, all the channels were drilled. This is one way to do it. But now that we can use 3D printing, we can have it look like in figure B. Here we can see that it makes sense to 3D print half of the injection mold. It didn't make sense to print all of it, and that's why we still have some drilled channels. But in fact, this resulted in the cooling time being reduced from 22 seconds to just 10 seconds. So you may think that that's not a lot, but in fact it's 55%, and that means that you can go from producing 1500 parts a day to producing 2100 parts a day. That's an increase of 40% for what the same machine can produce only with a 3D printed injection mold. Next up, we'll look at mass customization, where we can 3D print parts that perfectly fit the individual person. So what is mass customization? Well, this is when we design products that perfectly fit their function. And as the function changes, we can also quickly change the products. This means that we often get some better solutions and that there are often a much better fit. This is really interesting when we look at parts that need to fit the human body. So if, for instance, you needed a custom fit bike helmet, then you would be able to 3D print it. One of the industries that have really seen an impact from using 3D printing is the hearing aid industry. Towards the end of the 1990s, you went from modeling these hearing aids and then making them by hand to now 3D printing them. The way you make these hearing aids is that you take a wax cast of the person's ear, then you scan it and put it into the computer, and via a preparation program it goes to the 3D printer where it's printed, often on an SLA printer. Then you get the finalized print, you add the electronics, and then the product is ready for the client. This means that you've saved a lot of manual hours in the manufacturing process by 3D printing these hearing aids. So the hearing aid goes outside the body, but using metal 3D printing we can actually start to print parts that go inside the body as well. In this example, it's a hip socket that's being 3D printed. The hip socket consists of two 3D printed parts. In this picture to the left we see the socket itself, and the surface is perforated and has kind of a lattice structure. It's because of this lattice structure that the tissue inside the body ties better to this type of prosthesis than if it was a blank surface. And it's because of this that there's a huge potential in 3D printing parts for humans using metal 3D printing. With 3D printing, it's also possible to achieve some new thermal properties with materials that you weren't able to use before. So what is thermal when we're talking 3D printing? Well, it's a component's ability to absorb or give off heat. And if we look at the formula in the top right corner, it demonstrates pretty well that the amount of heat that can be transported depends on the size of the contact layer you have and how thick the walls are that need to transfer the heat. And if we look at the examples of 3D printing in the bottom, then we can see that 3D printing can make some pretty amazing geometries with some large surface areas. And that's why it's interesting to use 3D printing as a heat transferring source, either to cool or heat things. One of the places where we can utilize 3D printing to produce some thermal components is, for instance, a CPU cooler for computers. What you want from a CPU cooler is essentially that it's as efficient as possible, as small as possible, and weighs as little as possible. So if we look at a cross-section of a conventional cooler, it looks something like this, where we have some coolant coming in and some coolant coming out. EOS then looked at this and asked, how can we optimize this cooler? And they did that in 8 days, and they came up with this solution. Again, we have fluid coming in and fluid going out. But as we can see in the bottom, there's a large cavity with coolant all along the bottom plate that faces the CPU. And if we look at what came out of the printer, then it looks something like this. This one is printed in copper, which has very good heat transferring properties. And if we look at the results from this project, then in 8 days they actually managed to get on the same level as a high-end CPU cooler. And where they really managed to make an impact was in terms of weight. So we went from 407 grams to only 107 grams, and the volume has been reduced to a fifth. So you may think, how interesting is this? It's actually pretty interesting because all this either goes inside our very small laptop or it goes inside a huge server station where space is very costly. So the smaller, the better. The next case is an industry case that focused on whether we could produce headlights for cars with cooling for the LED bulbs. On top, we have the conventional part, and below we have the 3D printed version. And what's really interesting about this case is not only that we can optimize the cooling, but also that we can stack the parts in the build platform. This means that we can fit 384 parts in one build, and this shows that we're able to produce just as many with 3D printing as we could conventionally. So this is quite interesting. We took the design and looked at the thermal properties we needed, but we also optimized it for the 3D printing process. And actually, when it comes out of the printer, it's ready to have the LED mounted. Now it's time to look at how we get more functionality into our 3D printed parts. So what is functionality when we talk 3D printing? That is when we're able to get more functions into our parts than we were able to conventionally. For instance, as the clever pigeon says, it could be something that affected performance, something that affected how easy it is to service the process in which the component is part. For instance, does it help optimize the process? So we'll look at some different cases where we utilize the extra functionality that 3D printing gives us. The first case that we'll look at are flexible fingers for a robot gripper. The advantage of these grippers are that we can pick up things very gently, as we can see in the picture to the right, where we pick up an onion. Furthermore, as we can see below, it's possible to get in very narrow spots and pick up components without moving the gripper very much. If we look at how this is printed, then it's actually printed in one part with hinges built in so it's able to move, and it would have been very difficult to manufacture this conventionally. The next case we'll look at that utilizes the functionality of 3D printing is a spatula for folding dough. You may know the scenario from home where you're working with a spatula and then when you flip dough over, the dough sticks to the spatula. Here, you've solved this issue by making holes in the spatula and then blow air in through the end so the dough will release much quicker. Since this spatula is for industrial use, it needs to happen very quickly, so there are a lot of holes and it's pressured air that's coming through. This case has actually reduced the amount of parts needed to make this spatula with 80% if you compare to conventional manufacturing. Plus, there are no weldings in the area that's in contact with the food. So this is a really good example of how you utilize 3D printing to add more functionality to a relatively simple part. The next case that we'll look at is one of the more advanced ones, and it's really gained some extra functionality from using 3D printing. These are pickups for record players that are produced by the company Autophone, which are world leading in this area. The special thing about these pickups is that they are 3D printed in metal using the powder bed fusion technology. And since we're using this technology, then we can make cavities with loose powder in it. And the interesting thing about that is that the loose powder has a dampening effect on the pickup, which means that you'll get a much more pure sound through your speakers. In fact, the sound is so pure that these pickups have been named the best in the world. Next up, we'll look at lattice structures. So if we look at what a lattice structure is, then it's a series of points that are arranged in a distinct pattern. And for the sizes that we're looking at here, it's only the 3D printing technology that can be used to make these solutions. As you can see in this figure, lattice structures can be elastic and bend in all different directions. And this is really interesting because we can use them for lightweight solutions or for functionality that weren't possible before. We'll illustrate that with a few cases. This case is one of the stranger ones, where Adidas has decided to make a running shoe that's harder to run in. So what they did was to design a lattice structure that actually absorbs energy, which makes it harder to run. Therefore, it'll feel like you're going for a run in the sand dunes when in fact you're only running on asphalt. You can see that Adidas has invested heavily in 3D printing when you visit their website. Here you see quite a few shoes with 3D printed soles, and they're all available on the market today. One of the places where lattice structures are also interesting is when we start to talk infill of our 3D printed components. If you have an FDM printer, you know all about them making honeycomb structures, so it's not necessary to print a massive part. This is mostly just to save material, and the part I have here is the crank box for a bicycle, because the bicycle industry has also started to look at 3D printing. Here you have some outer geometries that you want, and you have some inner geometries, and essentially you just want the parts to be as stiff as possible and as light as possible. And this is really interesting when we start to talk about metal printing, because here you can also print lattice structures that mainly have the function of stiffening the part. You cannot talk about 3D printing without also talking about lightweight. So why is lightweight interesting? Well, if we look at the financial perspective, then all the material that we add when printing adds a cost. So the more that we can reduce the mass of our part, the cheaper the part will get. And I guess that's something we're all interested in. Also, this often leads to us getting a lighter part than if we were to design and manufacture it conventionally. If we look at the formula in the top right corner, we can see that the energy needed to move a mass at a given speed is quite depending on the mass. So if we can reduce the mass, we need less energy to move it. If we apply this to a motorcycle like the one we see here, then this one has a topology optimized frame which is lighter than if you were to manufacture it conventionally. This then means that you need less fuel to move this motorcycle at the same speed. The first case that we'll look at here is a knife which is mounted on a robot in the food industry. And if we look at the original knife, then we can see that it consisted of 20 parts and weighed around 800 grams. 800 grams may not be a lot, but by optimizing it, we managed to get it down to 80 grams and consisting of just one part. By 3D printing the knife, we also get a shorter delivery time, and the production price is reduced by 60%. Furthermore, it's interesting to note that by reducing the mass of this knife, then we can increase the speed of the robot. This actually means that we can go from having 8 robots to only having 6 robots running the same amount of dough. One industry where weight means a lot is the bicycle industry, as we mentioned previously, because the lighter you can make your bike, the less energy you need to move it, say up a mountain. One example is from SRAM that looked at optimizing their bike crank arm. This has been designed so it doesn't need support material when being printed, and it's printed in titanium. By printing in titanium and by topology optimizing it, it's now twice as strong as a conventional bike crank arm, and it's 20% lighter. So this is really interesting that you can actually save this much weight in such a small component. One of the really interesting things when we're talking 3D printed parts is the design freedom that we get compared to conventional manufacturing. So what is design freedom? It means that we have some new limits of what is possible to manufacture, and that gives us some new possibilities that we didn't have previously. So if you have a brilliant idea in your head like the guy to the right, well, then there's actually a pretty big chance that it's possible to manufacture it. One area where the design freedom of 3D printing is interesting is in the food industry. Here it's the company Marel that makes machines for food processing. The example that I brought here is a robot gripper, and when you first look at it, it doesn't look as if it utilizes this design freedom. But then if you look closer, you can see that there are roundings practically everywhere, and that makes the part easier to clean. We can also see that the part is 50 centimeters long, so if we were to make it conventionally, then we would maybe need to mill it out. This would require a big block of plastic, so we would need to mill away a lot of material. You could also have it consisting of several different parts, but then you would have assemblies in a food contact area, and that's not ideal either. So 3D printing really is the best solution. Marel has really adopted 3D printing and the design freedom that comes with it. And here we can see a selection of all the robot grippers that they have designed for the 3D printing technology. This is a case that I really find interesting. Michelin saw the idea in using 3D printing for their injection molds for casting tires, since they could get some additional functions and better grip out of their tires by using these molds. In fact, they've been doing it since 2013, so they've been at it for a while. They also made a small 4-minute video where they explain why and how they use 3D printing, and you'll find a link for that at the end of this presentation. The last feature that we'll look at here is computer-aided design, because without a computer there wouldn't be anything called 3D printing. The most common way to construct and design a part is by designing it in a 3D CAD program. It could, for instance, be one of the programs that I've listed here. But since 3D printing allows you to print some very advanced geometries, we're starting to see more and more new programs where you can actually have the computer generate the design. We'll take a closer look at that in the next couple of slides. One of the tools that you can use on the computer to generate a design is topology optimization. Here, the computer calculates how much mass we can remove but still have the part last. This could look like the figure below, where it's optimized so you get some more natural shapes, kind of like bone structures or geometries from nature. With topology optimization, we looked at how much material we could remove from a part, but with generative design, we look at how we can connect different dots with the least amount of material. In this video, you can see an example of how it works. In my opinion, this is probably one of the coolest ways that you can design a robot gripper. This is a website where you add the part that you want to optimize, and then you check where you want the suction cups to be, and the software generates a robot gripper like you see in the picture to the right. When you're done, you just press order, and then they'll print it in SLS for you, and you get a robot gripper that perfectly fits the part that you need to handle. One of the biggest challenges when we're talking 3D printing is actually finding out which parts it makes sense to print and which it doesn't make sense to print. The company Caster has made a software to analyze your entire collection, and I'm sure this is something we'll see more of, where we get digital solutions to help you make the right choices about when to print and when not to print. Finally, here are some links for the different cases if you want to learn more about why it makes sense to 3D print them.